where sudden spikes of radiation can turn deadly.
If we were walking around on the surface of the moon, I would say our number one concern should be solar flare. The sun erupts. The protons coming from that flare could kill an astronaut. There have been several flares over the last couple decades, which if we had had astronauts on the moon just walking around in a spacesuit would have been lethal for them.
On Earth, we're protected from most radiation. Earth's atmosphere and magnetic field are like a protective fence, letting only a fraction of particles through. On the Moon and Mars, you are directly in the firing line. The Moon has no atmosphere or magnetic field. Mars has very little atmosphere and only weak localized magnetic fields. NASA takes the solar flare threat seriously because it has already come close to killing Apollo astronauts.
The Apollo lunar landing crews were quite fortunate. In 1972, in August, there was a major solar flare. There was what they call the Great Solar Storm that happened to just take place in between the Apollo 16 mission in April and the Apollo 17 mission in December of that year. Had that occurred while there was a crew on the surface of the moon, they would have been dead.
The effects would be similar to certain people who died in Hiroshima and Nagasaki, those who were not killed in the initial blast, but were overwhelmed by the extreme radiation dosage within several seconds. An astronaut caught in that situation will have little time to react. A flood of deadly particles penetrates the body, killing all of the astronaut's cells in a few brief moments. So it's no surprise that space colonists will need to be constantly on alert.
We're going to need weather reports, but they're going to be space weather reports. We're going to need satellites monitoring the sun, giving us advance warning of flares. The light from the sun takes only 8 minutes to reach the moon. Coming behind it would be the particles, the lethal radiation. You'd have minutes, half an hour, that sort of time frame before you wanted to really be in a shelter. Such a storm might last for a couple days.
One option for protection is living underground. But don't let the barren terrain fool you. The Moon and Mars are still active bodies where natural disasters like those seen on Earth can strike.
I'm here in the Mojave Desert in a cave created by a lava flow, underneath 5 or 6 feet of rocks. Well, being underground in a cave may be an option for habitation on the Moon or on Mars. On the surface of the Moon and Mars, there's radiation from the sun, there's cosmic radiation. On Mars, there's dust storms. If we're underground, well, we're safe from those hazards, but we have other hazards. Imagine being in this cave when there's quakes, rocks falling down, crushing us, pinning us.
A Moon or Mars quake could also threaten an above-ground colony. The Moon and Mars don't have tectonic plates like the ones that cause most of Earth's quakes and volcanic eruptions, and there are no signs of active volcanoes. But the Moon and Mars do have hot cores. So as the pressure from that heat heads to the surface, the shaking starts. And where there's quakes, there's often another disaster.
Just recently, we've seen a landslide occurring on Mars. It was captured with the cameras in orbit. So we know this does happen. And that can be hard to predict. We might put our base someplace which appears perfectly safe, and then a few years later realize that there's a landslide hazard.
Scientists are still unsure what started the 2008 landslide near the North Pole of Mars. It was in an icy area, and researchers believe most of the slide material was ice. That's just the type of place a colony might be located to take advantage of converting the ice to drinkable water. Even a distant quake could still trigger a slide near a colony. But what if a hidden fault line is running right under the buildings? In the future, space colonists living on the Moon or Mars will have plenty of threats to deal with, including natural disasters like moonquakes and Marsquakes.
They're not active the way we're used to on Earth. They're active in different ways, and there may be unexpected ways that they could cause problems for us.
Since our current knowledge of these other worlds has literally only scratched the surface, it's possible that in the future we could locate a base right over a fault line without realizing what's below. And since weight is always an issue when carrying things into space, the lightweight buildings could be quite vulnerable, especially the outer layer.
If anything happens to that protective layer, that's trouble, very rapid trouble, as the gases stream out of the habitat. You've got to have a very efficient and quick procedure for getting into a spacesuit to survive that sort of decompression.
Death would not be instantaneous if oxygen and atmospheric pressure inside the colony are suddenly lost. On Mars, there is a thin atmosphere, although it's not breathable, since it's mostly carbon dioxide. On the Moon, there is only the vacuum of space. But you'd still have a chance, as we've learned from industrial accidents in vacuum chambers on Earth.
Exposure for maybe a minute or so is survivable. Now, if you stay in a vacuum long enough, there's not enough oxygen, so nitrogen that's saturated in your blood and your tissues comes out of solution and causes bubbles. That's decompression sickness. And also, if you hold your breath, you can get what they call pulmonary overinflation, and your lung ruptures into your bloodstream, and that's called an embolism. So there's multiple factors that can result in death from exposure to the vacuum of space.
Then there's the temperature extremes. Temperatures on the Moon go from a high of about 240 degrees Fahrenheit down to around 290 below. Mars can get just as cold. Although you could get lucky and have a nice 70-degree summer day. But without a breathable atmosphere, going outside without a spacesuit is still a very bad idea. Another thing above-ground space colonists will have to be on the lookout for is meteors. The craters on the Moon tell the story. It's an easy target.
We're relatively comfortable down here underneath these layers of protection. We've got a thick atmosphere which absorbs and burns up meteorites. We go to the Moon, nothing. There's no thick atmosphere. We are exposed to everything that space is throwing at us. We go to Mars, there's a thin atmosphere, but it's not anywhere near as good as the Earth. So again, we're exposed to what's coming in from space.
Smaller meteors that are only inches or fractions of an inch wide, known as micrometeoroids, will strike most often and without warning.
You're walking along the surface of Mars, and something the size of a grain of sand comes slamming into your spacesuit. That's going to be a serious problem. It's going to be a loss of the pressure in the spacesuit. It could mean loss of life of an astronaut. When we have lots of people doing a lot of work on other worlds, eventually that's going to happen. That's the equivalent of a lightning strike, a rare, possibly fatal event.
Micrometeoroids could also punch a hole through the wall of a colony building. Like space stations, colonies will probably be built in a series of sections or modules. And just as crews have had to seal off sections of a space station in an emergency, colonists will likely do the same. Large meteors will hopefully be tracked, so the colonists will know they're coming. But evacuation might not do any good. A nearby strike would still send out a deadly shockwave for miles. A 10-foot wide meteor hits with the explosive equivalent of 6,000 to 8,000 tons of TNT. Flying debris could also damage colony buildings beyond repair. And anything approaching a direct hit, there'll be little evidence that the colonists were ever there. It's unlikely that colonists would live anywhere near one of Mars's volcanoes. And the moon probably hasn't seen volcanic activity in the last few billion years. But even ancient remnants of volcanoes could still cause trouble for crews in vehicles.
Both the moon and Mars show evidence of volcanic flows. So we might expect to find there this sort of thing, volcanic caves. Now imagine driving along the surface, come across one of these, you're not expecting it, that could ruin your day, it could ruin your vehicle. You could be at the bottom of this pit without any way to get up. Even worse would be imagining one of these volcanic caves with a thin layer of volcanic rock on top of it. You move across on top of that, it gives, and down you go.
But not all colony disasters will be so dramatic. Simply running out of supplies is one of the greatest dangers. Since the moon is much closer, emergency supplies could arrive in a matter of days. With Mars, help is many months to years away, depending on how the planets are aligned.
On Mars, if something goes wrong and you lose some supplies, resupply from Earth can be 2 or 3 years away. You think you've got enough to last, you lose half of it through an accident, you're dead. It's a real problem. I think that means you're going to have more than what you need. You're going to have enough for 5, 6 years.
Living in space much closer to home, on space stations and longer shuttle flights, has already taught us a lot about the dangers of space. And fire is space crew enemy #1.
The reason fire is such a threat is because spacecraft traditionally have higher levels of oxygen than the atmosphere, certainly in higher concentrations, under pressure. They're also filled with electronic equipment. Electronic equipment puts out heat, and often there are sparks and arcs. It's a bad combination.
Luckily, designers have made it easier for crews to put out fires where all of those miles of wire lurk behind the control panels.
This is a mock-up of the Space Shuttle flight deck that we use for training of crews. If you look at the various panels we have, you will see small holes like this at various locations around it. And these are for fire extinguishers, so that if there is a fire behind one of these panels, you can put an extinguisher in there to extinguish the fire.
Andrew Thomas knows a thing or two about fires in space. While on the Mir space station in 1998, a fire suddenly broke out.
All the smoke was pumped right out into the cabin.
crews hurtle through space in their enclosed craft, desperate to maintain the Earth-like atmosphere inside. Out here, fire is one of the biggest threats. In 1998, NASA astronaut Andrew Thomas is on board the Mir space station with 2 Russian cosmonauts. Suddenly, a fire breaks out. Ironically, the fire starts while cleaning what's known as an air scrubber, one of the filters designed to remove exhaled carbon dioxide and other toxins from the space crew's environment.
All the smoke was pumped right out into the cabin, and so all of a sudden, the cabin in one part of the space station just became thick with a pall of smoke. And of course, all the air handlers then moved all that smoke around the spacecraft, so within about 2 hours, the entire spacecraft was completely filled with smoke. So we had to just wait for the air handlers to scrub all of this contamination out. And that took about 2 days. And we all manifested symptoms of the toxicity of that environment. When there's a lot of carbon monoxide at those levels, you have nausea, a certain amount of confusion, invariably a headache because you're oxygen deprived. It's just a very uncomfortable feeling.
The dangers of fire in space go beyond the fact that you can't open a window or call the fire department. Fire actually behaves differently inside a spacecraft in zero gravity.
What we are seeing is a candle flame. The bottom one is a candle in normal gravity. And as you can see, the flame moves up because buoyancy pushes the hot gases around the flame up. The top photograph is the same candle, but in the absence of gravity.
Columbia Space Park for the module. A mist burn will be initiated here in about 15 seconds.
The hot gases don't move up, and what you have is an spherical flame.
There's the flame. So here's the initial light off for combustion module 2.
So putting a smoke detector on the ceiling, like we do on Earth, doesn't work in space. Instead, detectors are located next to small suction devices that draw air and any smoke or other toxins toward the detector. To figure out just how dangerous fire is in space, Professor Fernandez-Peyo's team performs experiments in the University of California, Berkeley Combustion Lab and on KC-135 aircraft in short bursts of zero-G. In theory, fires in zero gravity should be less intense because the hot gases don't rise, which means cool air isn't drawn in at the base to keep feeding the flames. But they're finding that the reality inside a spacecraft is more dangerous. Air conditioning systems create small air currents. Those currents bring fresh air, or in this case, fuel, to the fire. At the same time, the low airflow and lack of gravity don't remove the heat as quickly as on Earth. The result?
This type of fires are hotter and more dangerous than in normal gravity.
And fire is likely to become even more of a safety hazard inside the new Ares Orion spacecraft being designed to replace the shuttle.
What they've decided to do was to reduce the pressure and increase the oxygen. And by doing this, they reduce the preparation time that it takes for the astronauts to go from the vehicle to outside of the vehicle. So what we're doing is we're testing materials at that proposed environment. We've learned that for the environment that they've chosen for the next generation of vehicles, things actually ignite about 20% faster than they would in the current environment.
The combination of high oxygen content and low airflow means just about anything can catch fire, even metal. In a worst-case future scenario, a space station crew is unable to quickly extinguish a fire. It grows too fast to seal off in a separate module. Even if they put on emergency oxygen masks, the heat of the flames will likely kill them. And if they're somehow able to survive the flames, the filtering system is completely overloaded. They are left to die in a toxic stew from smoke inhalation. The best chance of survival with an out-of-control fire is to abandon ship and return in a re-entry capsule if one is available. That was the key to the survival of the crew of Apollo 13. April 11th, 1970, the three-man crew launches into space. 2 days later, on their way to the moon, an oxygen tank suddenly explodes. The explosion causes a substantial loss of oxygen and damages the service module's electrical system. The crew is forced to live in the cramped lunar capsule.
Apollo 13 is the classic case of the failure that doesn't kill you. It happened at the right time. It happened when they were on their way to the moon, so they could use the lunar module as a lifeboat and get back to Earth. Had the same problem occurred after the lunar landing, when Lovell, Swigert, and Hayes were on their way back to Earth, there would have been nothing they could do. They would have been dead.
The threat of fire is especially high inside spacesuits. During spacewalks, also known as EVAs or extravehicular activity, the spacesuits need to be kept at low pressures. Working in a fraction of Earth's atmosphere is the key to flexibility.
If you had a spacesuit that was at 1 atmosphere, you would be like basically in a balloon, and you couldn't move.
With low pressure, just like a climber in the thin atmosphere of Mount Everest, astronauts need to breathe highly flammable 100% oxygen.
This is an arm from the spacesuit. It was burned up in a fire in 1980 at Johnson Space Center. Just doing some checkout tests, pressurizing the system with the 2 different oxygen sources. And when this fire occurred, it was, quite a shock. People were standing nearby it, and someone was supposed to be in the suit the next day for a manned test, and it could have been a fatal fire. Even as it is, this suit is worth, at the time, $3.1 million. And it also took NASA $20 million to recover from this fire in terms of redesigning the suit.
Extravehicular activity is dangerous for many other reasons as well. In fact, the world's first spacewalk almost ended in disaster.
Alexei Leonov did the first spacewalk that any human did in 1965. But in the rush to accomplish that space spectacular and thereby beat the Americans, the Soviets took some shortcuts on the safety of the cosmonaut. And so he blew up like the Michelin Man.
The suit became rigid. It couldn't handle the pressure differences between the breathable atmosphere inside and the vacuum of space.
The problem is you've got a spacecraft in the Soyuz capsule that he was flying that's very small, and the hatch for it is even smaller. Ultimately, his response was to let a little bit of the air out and just deflate the thing enough so that he could crawl back in through the hatch. But he will tell you that to this day, that he wasn't sure he'd be able to make it.
An astronaut having, like Leonov, to let the pressure out in order to be able to maneuver in it is in the same situation as a diver ascending from deep water too quickly. Nitrogen bubbles will form in your bloodstream and not only be painful, they'll kill you.
And during EVAs, a simple thing such as an unsecured tether or a misfiring emergency thruster can also spell disaster. Being outside of a spacecraft on a spacewalk is the most dangerous thing an astronaut in orbit can do. One false move can be deadly, especially if that false move takes you away from the spacecraft.
There was an instance on one of the Russian space stations, the Soyuz, where one of the crew members was not tethered, and he was in the airlock area watching the other crew member, and he slowly started to drift out, and the other cosmonauts saw him and grabbed him. An untethered person in space Without appropriate propulsion system to get back would be very, very serious. I mean, basically, you're lost at sea.
Even with a propulsion system, it can fail or run out of its limited propellant supply before the astronaut reaches safety. The astronaut will simply keep floating off into space. The International Space Station is unable to chase someone down, and if the shuttle were docked, it would take too long to undock and mount a rescue. In this nightmare scenario, the astronaut will likely have several hours of oxygen remaining to contemplate the end. As long as the suit is intact, pressure will not be an issue. Either the oxygen will run out, or the system, which removes exhaled carbon dioxide, will stop working. Either way, the astronaut will suffocate and continue floating into the emptiness of space. The same micrometeoroids that can devastate space colonies also pose a lethal threat to spacewalks and entire spacecraft. Plus, in low Earth orbit, these rocky little gremlins have company, space junk. And all of these things are racing around at over 22,000 miles an hour. At these speeds, objects that are only a fraction of an inch wide can be deadly.
A micrometeoroid flying through space is a lot like a golf ball flying through the air, with these differences. The micrometeoroid is much, much smaller. And because it travels at hypervelocity, it's far more destructive when it hits. If a micrometeoroid hits your spacesuit, it's going to put a hole in it. You don't have reach or the ability to patch or fix it, unless you've got a fellow astronaut right there. You're going to die. Your air is going to leak out fairly quickly. It's going to gush out. Your blood's going to boil. That's going to be it.
And what causes blood to boil? Well, in space, boiling blood has nothing to do with heat. It's all about the sudden lack of atmospheric pressure.
The idea that blood boils is really a misnomer. The liquid in your body goes from a liquid state to a gaseous state.
There have been many tales about what happens to an unprotected person in outer space. Here's the real story. As the vacuum of space fills the spacewalker's leaking suit, the liquid parts of the tongue and eyes begin to bubble, along with all of the saliva, internal fluids, and blood. As the blood turns to gas, oxygen no longer travels to the brain or anywhere else. The brain shuts down within about 15 seconds, leaving the victim unconscious. Soon after, the rest of the cells in the body die. Temperature extremes could also play a role, since the sunlit areas of space reach 250 degrees Fahrenheit, and the shaded areas quickly plummet to 250 degrees below zero. And just how big a hole is too big for a spacesuit?
You're really asking a very small amount of material to stop a particle that could be coming in at 7 kilometers per second. You can see the entry hole from the test, and it has many, many layers, ending with what's called the bladder, and this is a pressure retaining layer. That's about a 2 to 3 millimeter hole, a 4 millimeter for an EVA suit on the soft goods. This material would be considered catastrophic.
Luckily, no one in space has ever suffered this fate. Impacts can also cause trouble in sneakier ways. So NASA goes to great lengths to simulate different types of micrometeoroid damage down on Earth. Researchers inside the hypervelocity building of the White Sands Test Facility in New Mexico create impacts using compressed hydrogen gas guns. These guns definitely bring the heat, shooting objects up to 19,000 miles per hour at shuttle and space station parts to assess the damage.
At that velocity, you can get from Los Angeles to New York in about 8 minutes. The testing that we're going to perform today is on an International Space Station handle that the astronauts use on the outside of the space station in order to transverse around the space station safely. Several astronauts have cut their gloves severely. This is a great concern to NASA because when they designed the space station, they are very careful to eliminate all sharp edges because you don't want something snagging the astronaut spacesuits and creating a hole and ending a mission.
technicians mount the handle in the target chamber, place the tiny 1/32 of an inch wide projectile within a holder that will disintegrate once fired, then add gunpowder to the breech.
We take gunpowder and propel a piston which compresses hydrogen gas up to about 100,000 psi. It's that highly compressed gas that accelerates the projectiles from 0 to 19,000 miles per hour. We use 3 different types of cameras. One takes a snapshot, another one takes a film, and the third type is a digital camera which takes 16 frames at 200 million frames per second.
The technicians retreat behind a blast shield and prepare to fire. The chamber is cleared of oxygen and other gases to simulate the vacuum of outer space. Now, the moment of truth. How much damage did this simulated micrometeoroid cause?
Even though it is a small impact, there's enough of a lip with enough structure so that an astronaut could catch their glove on such a lip and cause a tear in their glove.
And if a projectile only 1/32 of an inch wide can cause this type of damage, you won't believe what a larger object can do. At the NASA White Sands Test Facility in New Mexico, researchers load small projectiles into huge guns. The projectiles simulate micrometeoroids and space junk. They slam into spacecraft parts at up to 19,000 miles an hour, creating disasters on Earth to better understand disasters in space. At such incredibly high speeds, a very small object can cause very big trouble.
I'm standing inside of our largest target chamber of our 1-inch gun. The gun is 175 feet long and can launch up to a 3/4 inch size projectile. I'm holding a target that was impacted with a 5/8 inch projectile, and as you can see, this is the entry hole, and it went all the way through the test article. An impact of this size would be a catastrophic event in space.
The only hope the International Space Station crew would have for survival is to put on emergency breathing masks and head to the re-entry capsule. An object less than an inch wide would have forced them to abandon this multi-billion-dollar facility. That type of scenario is the reason why crews are constantly adding extra layers of protection to the outside of the space station. For another type of space collision, we have only ourselves to blame. In 1997, a Russian cosmonaut had trouble guiding an unmanned cargo craft to its docking point with the Mir space station.
Now, we know in aviation that 70% of the accidents are human-related, so it wouldn't surprise you to think that humans have also a big role in accidents and mishaps in space. The Mir collision actually was because a crew member complained that he wasn't trained enough to do the rendezvous, and the ground control team said, well, you have to do it anyway. The hit occurred and it caused a leak in the cabin pressure, so now they started to lose cabin pressure. And then the space station started to tumble because it was like pool balls. One hits another, it causes it to move. So even a minor thing, just the control of a rendezvous and docking could have almost catastrophic consequence.
But the disasters that have happened in space still pale in comparison to the disasters of getting into space and returning. There is a saying that the first 50 miles and the last 50 miles are the most dangerous part of any mission. The 1986 Challenger launch disaster and the 2003 Columbia re-entry tragedy make that clear. But if we're ever going to travel beyond our solar system, we're going to need to move beyond our current rocket technology. One possibility that both thrills and terrifies is known as an antimatter engine. Inside massive particle accelerators, scientists have created minute amounts of antimatter which is made of atoms that have the opposite charges of normal atoms. So with antimatter, the electrons are positive and the protons are negative. When matter and antimatter come into contact, they annihilate each other, releasing tremendous amounts of energy.
Antimatter engines have a 100% conversion rate of matter into energy. Realize that even an atomic bomb is only 1% efficient. Only 1% of the mass of an atomic bomb is converted to energy. In an antimatter engine, we're talking about nearly 100% of the mass converted into energy. It is, for the next century, the propulsion system of choice. But there's a problem.
A teaspoon of antimatter might be able to propel us across the solar system. But that same teaspoon also has the power to destroy an entire city. And once a spacecraft is out in deep space, simple accidents can suddenly tip the balance from life to death. As we venture to Mars and beyond, with journeys lasting years at a time, the chances of becoming stranded in space will become much greater.
For example, on a flight to Mars, what if a micrometeoroid punches an oxygen tank? What if you just are simply running out of breathable air? There is nothing you can do. You can die graciously is what you can do, however long it takes.
Another source of disasters, especially with journeys measured in years, is something that many people overlook.
One thing we forget is our fellow man, our fellow astronauts. If you're cooped up in this tiny little space capsule for, let's say, a year at a time going to Mars, or years going into deep space, you can go crazy. You can get claustrophobic. The guy next door could really get on your nerves, and you want to strangle him after a certain point.
Although the incidents aren't highly publicized, crew members have had problems getting along in the past with dangerous results.
There was at least one Soviet space station crew of the 1970s that didn't get along pretty famously and actually supposedly had a fist fight. These stresses are going to manifest themselves on these long-duration missions. Anybody who thinks they aren't is fooling himself.
And to make things even more interesting, Russian cosmonauts supposedly have firearms stowed on board as a precaution after an extremely off-course landing in 1965.
The crew landed up in the woods in Siberia and were there for about 3 days. And they had to fight off wolves until they were rescued. After that particular mission, the Soviets decided that they were going to put a sawed-off shotgun in every Soyuz capsule in case something like that happened again.
The cosmonauts are now rumored to have handguns stored in emergency kits. But no one is eager to offer any official details of guns in space. And the risk of having a weapon aboard isn't just a concern if tempers flare.
There is actually a documented case of a payload specialist who flew on a shuttle flight, whose experiment failed, and he spent his whole life getting this experiment ready. It failed, and he actually talked about killing himself. And the crew themselves actually tried to protect him and guarded the hatch so he wouldn't kill them.
Even with all of the space travel lessons learned so far, one thing is clear. Nothing can completely prevent disasters from striking in the future.
If we're going to continue human spaceflight, we have to accept the risk because it is a very dangerous occupation. But we have to manage the risk, and that's going to require good technical people and good leadership.
But just as surely as disasters will strike, there is another certainty when it comes to manned space exploration.
I think we have a gene for exploration, a gene for discovery. Not only is it good for our evolution, because we find new avenues to reproduce and to colonize, but I think it's also inside the spirit of human beings to want to know what's out there. Is it possible to reach areas that we've never been before? And the thrill the thrill of being the first person to explore new terrain, that's fantastic.
In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe. Streaking through space, light is the fastest thing in the universe.
It could circle the Earth 7 times in 1 second.
As it reaches us across vast distances, it reveals the history of the cosmos.
We're able to look back in time.
Light travels at 186,000 miles per second. Its speed is an ultimate barrier. Nothing can go faster.
We have never, ever broken the speed limit.
But is the answer final? Will spaceships ever speed faster than light? Is it even worth trying?
To give up without trying is just giving up.
It can neither be touched nor felt. It is an abstract quantity of immense impact, the rate of motion at the very heart of all existence, the fundamental linchpin of the universe that we call light speed. Planet Earth, where speed is in demand, the fastest people, vehicles, and technologies seem to crawl in a cosmos where light speed is king. More than king, the speed of light is the cornerstone on which the universe is built.
There's a famous saying in physics, which is that the speed of light is not just a good idea, it's the law.
The speed of light is one of the most important speed limits in the entire universe.
The speed of light, 186,000 miles per second, is just incredible. I mean, if light traveled in a circle around the Earth, it could circle the Earth 7 times in 1 second. That's an incredible speed.
That incredible speed is the first thing we encounter when confronting the phenomenon of light. To say it is fast is a colossal understatement.
It's amazing to me that when I talk on my cell phone, I can talk to somebody clear across the country, and I'm not really aware of any time lag. And that signal is going from my phone to a tower, up to a satellite, back down, and it seems instantaneous. So we really take for granted the speed of light could practically be infinite to us.
Physics professor Clifford Johnson of USC is an avid bike rider. Circling a track, he considers trying to cover the same 186,000 miles that light does in 1 second. He'll find, however, that his work will be cut out for him.
To travel the distance that light moves in just 1 second, it would take me 22 months on a bike moving at 12 miles an hour, cycling 24 hours a day.
But the speed of light, in relation to the speed of life, makes our world work in just the way we've come to expect.
One of the beneficial effects for humanity of having the speed of light be as fast as it is that what you see is what you get.
Light speed makes everyday experience virtually instantaneous. When the light bulb goes on, you see it right away. Anything that happens around you registers immediately. And certain experiences make it crystal clear that light travels faster than anything else, including sound.
One interesting consequence of the great speed with which light travels is that you see a flash of lightning essentially instantaneously, but you hear the thunder only later on.
But light speed has its limits when stacked up to a place as large as the universe.
We think that the speed of light is unimaginably fast on a human scale. However, In astronomical terms, it's actually kind of pokey.
And so it's ironic that when the Apollo spacecraft blasted into space, traveling at what seemed an amazing 25,000 miles per hour, the speed of light proved frustratingly slow when it came time to talk to astronauts 236,000 miles away on the lunar surface.
So when the astronauts were on the moon and people asked Neil Armstrong, "Hey, Neil, what's it like up there?" Several seconds went by between the question and Neil Armstrong's answer.
Neil, this is Houston, radio check, over. Hi, Roger. Houston, loud and clear. Roger, out. Loud and clear, Houston. Roger, buzz.
And those several seconds were not because he was thinking about the answer, but rather because it took 1.3 seconds for the signal traveling at the speed of light to reach Neil from Mission Control, and another 1.3 seconds for his reply using radio waves to come back. And that's 2.6 seconds without even thinking.
Okay.
The 1.3 seconds it takes light to travel from the Earth to the Moon is pocket change compared to other celestial bodies. Light from the Sun, for instance, takes more than 8 minutes to get to the Earth.
If the sun were to disappear right now, if the sun were to suddenly vanish, it would take 8 minutes before we would even feel the shock wave and see the effects of a disappearing sun.
The limits of light speed also make communicating with Earth's far-flung spacecraft a special challenge. It takes up to 44 minutes for signals to travel back and forth to the probes exploring Mars. More than 3 hours to Cassini at Saturn. And over 29 hours to Voyager 1, the most distant of all, now heading out of the solar system. Still, these distances are trivial on a cosmic scale. We can almost understand the 10 billion miles separating Earth from Voyager. But what's next? The nearest star is a red dwarf named Proxima Centauri, nearly 25 trillion miles away. That's 25 followed by 12 zeros.
I am often asked a question, how can you as an astronomer really comprehend these vast distances, these huge numbers? And the answer is, I can't. The human brain really doesn't wrap itself around numbers that big. Occasionally, I actually write out how many zeros there are in kilometers from here to a galaxy, just to see how huge that number is. But in reality, of course, as astronomers, we would be spending all day writing zeros unless we came up with a better unit to use. And that's what a light year is. A light year is approximately 6 trillion miles. It's the distance that light travels in 1 year.
Using light years to describe distances opens up another dimension of light speed's character. Think of it. Sirius, the brightest star in the sky, is 8.6 light years away. That means we see it not as it is today, but as it was 8.6 years ago. We see the bright star Vega as it was 25 years ago, and the red supergiant Betelgeuse as it was 500 years ago.
It's a wonderful gift of nature that because it takes time to travel, we're able to look back in time. The further out we look in distance, the further back in time we look. We would have no idea what our cosmic history was if the speed of light traveled instantaneously.
Laura Danley is curator of the historic Griffith Observatory in Los Angeles. With light's ability to take us into the past, she's assembled a stack of photos that tell light speed's story of the universe in snapshots, looking back in time to its beginning, more than 13 billion years ago, to the present day.
I'm putting together a scrapbook of the history of our family of galaxies, and that shows all the galaxies that we can see with our telescopes as far back as we can see with our telescopes.
Each photo in this album, then, shows something in the universe with a look-back time equivalent to its distance in light years. The famous Crab Nebula, 6,500 years ago. the galactic core, center of the Milky Way, 26,000 years ago. And the Andromeda Galaxy, our next-door neighbor, 2.5 million years ago. But practically yesterday on a cosmic scale.
I love this cluster.
For almost 90% of the look-back time, the album is filled with common galaxies. Common, yes, but intriguingly diverse.
These two are colliding. You can see one going what appears to be right through the other. And there's a lot of drama in the way galaxies evolve and the way they interact with one another. So this one would be, well, it's only about 500 million light years away.
As Danley places each shot in the album, a bigger picture begins to emerge. Adult galaxies have been the main characters, evolving in all their variety for the past 12 billion years. But the cosmos also has its childhood photos, showing galaxies when the universe was a mere toddler.
These are actually very interesting galaxies at about 11 billion light years away. These compact galaxies represent what might be a two or 2.5-year-old child, just really learning how to walk.
But even these galaxies have their younger brothers and sisters. This spectacular shot shows a gravity lens, a cluster of galaxies 2.2 billion light years away that bends light, allowing us to see much further in space and time. The lens reveals a tiny speck identified as one of the earliest galaxies we can see, as it was 13 billion light years ago, still an infant in the evolving universe.
Galaxies, when they were babies, really don't have a lot of distinguishable features. They're kind of blobs. They don't really have a lot of structure.
The universe as a whole was something of a blob at the beginning of its life, too. What we see of that time are the first light waves in history, reaching us only now, 13.7 billion years after they flashed into existence. We see them in the picture of an afterglow from the Big Bang. And they are known today as the cosmic microwave background radiation.
The cosmic microwave background radiation is the most distant thing we can see. It is, in a sense, the picture of the baby upon delivery.
NASA's all-sky picture reveals a glow that is uniform everywhere we can see. The universe as it was in a cosmic moment after its birth. But here, our view comes to a sudden halt. What we can see of the universe is limited, not by the size or power of our instruments, but by the barrier of light speed itself. How can the fastest thing in the universe make us blind to the infinity of space? Knowing that light speed is 6 trillion miles per year gives us the light year, a convenient shorthand for talking about the huge distances in the universe. But it's just as important to understand that light speed at 6 trillion miles per year is an ironclad constant.
The speed of light is so constant that the universe actually changes everything so that you never see it going any other speed. So the speed of light really is the measuring stick of the entire universe.
In fact, the constancy of light speed results in an amazing tool for measuring distance in the vastness of space. The tool is called redshift. It happens as light between galaxies travels at a fixed speed. When the space between the galaxies expands, the light racing between them gets stretched, turning red in color.
As light goes from one galaxy to another, from a distant galaxy to our own, for example, that light gets stretched along with the stretching of space. And that causes intrinsically short wavelength light, like blue light, to gradually become long wavelength or redder light. That fundamentally is the cause of the redshift that we see in the spectra of galaxies.
How does the redshift turn into a way to measure distance? It's all because of an astonishing discovery made in 1926 at the Mount Wilson Observatory outside Los Angeles.
Being up here on Mount Wilson is always a thrill for me because it was actually right here at this location that our view of the universe entirely changed. It was here that Edwin Hubble found out the universe is expanding. And that was an amazing thing. He wasn't expecting it. Nobody thought that was the case. And it changed everything.
Seeing red shifts everywhere, Hubble found that all of the universe's galaxies were moving away from each other, which we now know is caused by the expansion of space itself. As seen from the Earth, a galaxy doesn't look like it's moving away, but we know that it is because its light is red-shifted. A galaxy moving away at low speed has a slight redshift. A galaxy moving faster has a larger redshift. But Hubble found that those faster-moving galaxies are also farther away. That meant the greater the redshift, the more distant the galaxy. By seeing how fast space is expanding and working the math backwards, cosmologists have been able to estimate the age of the universe. Combine that with light speed, and you have a major brain twister.
The universe is such a huge place that the light travel time really becomes important to us. We believe the universe began about 13.5 billion years ago. That means the farthest in any direction we can look is 13.5 billion light years. There hasn't been enough time for light to travel more than that.
It's called our light horizon, a sphere 13.5 billion light years in all directions, containing everything we can see. But that's where the brain twister comes in. Does space end there?
We have no reason to believe that the distance we can see is the entire size of the universe. In fact, it might be much bigger than that. It's just that with light travel time, that's all we can see. That's our horizon.
So consider this conundrum. Astronomers in a galaxy at one edge of our horizon can't possibly see any galaxies on the other edge of our horizon. But they can see galaxies 13.5 billion light years in the other direction. And so can astronomers at the edge of their horizon, and on, perhaps to infinity. As for astronomers on Earth, light speed has them trapped.
If we ask what is happening beyond our light horizon, we have to face the fact that the speed of light really is a barrier. We've never seen anything beyond our light horizon.
Can we take comfort in the fact that there is so much to see inside our horizon? This breathtaking shot is the Hubble Space Telescope's ultra-deep field. It's a massively detailed photo of an area of the sky 100 times smaller than the full moon, yet containing 10,000 galaxies, some whose light has been speeding toward us for 13 billion years. Beyond that is the cosmic background radiation from just 400,000 years after the Big Bang. In NASA's color-coded picture, the radiation's glow is pure green, representing a distribution of matter so uniform, its temperature varies no more than 1/50,000th of a degree. Nothing in human experience is even close to this kind of uniformity. In fact, astronomers believe the universe should really be very different.
By rights, the universe should be lumpy. If you look in this direction and you look in that direction, you should see two entirely different concentrations of matter, different temperatures, but it's extremely uniform. Therefore, we have a puzzle.
The puzzle has its roots at the universe's birth in the Big Bang. If everything flew apart from the beginning, why shouldn't it be uniform?
No kind of explosion that we know about leads to that kind of uniformity. If you imagine an ordinary explosion, an atomic bomb, a piece of TNT, it's not really uniform at all. There's a piece of shrapnel going off there, a piece of paper going off there, an extra piece of iron going off there. It's really very non-uniform.
So scientists believe the cosmic background radiation just shouldn't be as smooth a green as it is. We can find out why in an ordinary paint store.
Let's consider a universe that consists of different color cans of paint. In our hypothetical paint universe, we have a can of yellow paint and a can of blue paint. And at the instant of the Big Bang in this universe, the two cans of paint start expanding apart from each other. In our hypothetical paint universe, one side of it would look yellow, and the other side would look blue.
But as we've learned, the cosmos looks green, whether it's the paint universe or the real thing. The two colors of paint represent the different particles in the infant universe. To end up a uniform green, like the cosmic background radiation, they had to be touching. But when scientists first calculated the speed of the Big Bang, they concluded that it blew everything apart faster than the speed of light, meaning blue and yellow were too far apart, even at the instant of creation, for any mixing to take place.
Seeing a universe that's so uniformly green would be very strange. It would be like taking our can of yellow paint, pouring it out, and having it be green, then taking the can of blue paint, pouring it out, and having it be green as well. It's impossible.
This horizon problem can be solved by a theory that I've worked on called inflation, which is a twist on the Big Bang.
Inflation is now the widely accepted variation that makes the Big Bang work without the limit imposed by the speed of light.
Another way this could have happened is that our paint universe might have expanded only this far. The two cans of paint have enough time to mix and become uniformly green before the universe undergoes a sudden period of expansion that occurs faster than the speed of light. This would spread green paint all over the universe.
If this theory is right, the period of inflation is really the Big Bang that we observe. The other bang that happened before that becomes really a little bang. It's just a precursor to the real Big Bang.
Even today, the universe is expanding at high velocity, galaxies speeding away from each other so fast that they seem to violate light speed as the ultimate speed limit. The faster-than-light expansion of space sets yet another limit on what we can see from Earth, where the galaxies of the universe continue to rush away from us.
The galaxies that are relatively near to us, those that you can see easily, are moving away pretty fast. And indeed, the more distant ones are moving away faster. But the ones that are really far away, in fact, are moving away faster than the speed of light. And then there are the galaxies that you will never see because they started out so far away that the light from them will never reach you because the space is expanding faster than the speed of light.
Space itself, then, is the exception to the rule. It can expand faster than the speed of light. But everything inside it remains bound by Albert Einstein and his theory of relativity.
Albert Einstein is the cop on the block. You cannot break the light barrier. We physicists can accelerate particles to 99.9999% the speed of light, but we have never, ever broken the speed limit.
But we don't need to break the limit to experience the strange province of light speed. If the universe bends and stretches around the speed of light, what happens when we hit the accelerator and start to get close? For most of us, light seems simple and uncomplicated, a quality of nature by which we see the universe. Under the scrutiny of science, however, it becomes strange and bizarre.
Light is such a common thing in our everyday experience, and yet we have very little understanding of it, really. It's very weird. The speed of light is something that the entire universe bends around to accommodate.
We can begin to understand why the universe bends itself around light speed by joining physicist Clifford Johnson at a bicycle track, where a tennis ball will compete against a beam of light.
If I throw an ordinary object like a tennis ball, I can throw it at a given speed, and it'll go a certain distance.
This is the path of the tennis ball as Johnson throws it while he's standing still. It lands roughly halfway down the track. Next, he'll throw the ball again, but this time from a moving bike, with different results.
If I throw the tennis ball at that same speed while riding the bike, it'll go faster because it's the speed of the tennis ball plus the speed of the bike, and so it'll go further.
Compare the two tosses and the difference is clear. The ball goes faster and farther when thrown from the moving bike. It makes perfect sense. But now we put light to the same test, using the bike's headlight instead of a tennis ball.
If I'm standing stationary and I switch on the headlight of the bike, that beam of light that comes out of the headlight comes out at the speed of light. No other speed but the speed of light.
Suppose the beam was slow enough for us to actually see its motion down the track. We mark its position just a brief moment later. Next, Johnson switches on the headlight at riding speed, and the unexpected happens. In that same moment of time, the light travels exactly the same distance as before.
Unlike for the tennis ball, you don't add the speed of the bike to the speed of the light. The speed of light remains the speed of light.
The two light beams travel the same distance because light speed is constant and independent of the source's motion. It may fly against intuition, but it is a fact of nature. Every beam of light in the universe travels at the same speed in empty space, no matter how fast the star or comet or galaxy that emits it is moving. After scientists discovered this fact at the end of the 19th century, Albert Einstein did the math for the rest of us and developed his special theory of relativity, with constant light speed as its center.
Understanding the speed of light gave us a window into understanding the nature of space and time as we understand it now. We do not live in a rigid world where meter sticks and a clock ticking at regular intervals. We live in a flexible, stretchy, Einstein's world, relativistic world of space and time.
In common experience, the universe doesn't seem very stretchy to us because compared to light speed, we are moving very slowly. But when we crank up the velocity, things begin to change.
As you get closer and closer to the speed of light, all sorts of strange and marvelous distortions take place.
When we say that the universe kind of bends itself so that the speed of light is always constant, it's amazing how literally that's really true. As you move closer and closer to the speed of light, your time appears to slow down to an observer that's just sort of watching you go by. That's amazing.
When Clifford Johnson bikes around the track, he needs to be going about 56 million times faster than his current 12 miles per hour to get close to light speed. But suppose he could.
Imagine I were riding my bike close to the speed of light. Never mind whether that's possible or not. Just imagine that this was happening. My clock's running slow compared to the cameraman on the ground who's filming me. If I do that for a while, I'm going to age much more slowly than the cameraman who's on the ground. So that when I come back from the trip and come back and talk to the cameraman, he's actually much older than when I left him.
If this sounds like magic instead of science, there is proof in something that many of us experience every day.
A great example of Einstein's special theory of relativity and the fact that clocks that are moving relative to you run more slowly than your own clock, which is at rest, is the GPS system.
The global positioning system lets us drive our cars without getting lost.
Turn right.
GPS begins with a network of 24 satellites orbiting the Earth 12,500 miles above the surface. At any one time, the device in your car receives signals from at least 4 satellites and compares their light speed travel times to calculate an accurate location on the ground.
Drive 500 feet, then turn right.
The whole thing depends on super accurate clocks. And when the engineers designed the system, they knew the satellites would be orbiting at nearly 7,000 miles an hour. The speed is enough to slow down their clocks by a tiny fraction of a second. The engineers have factored all the relativistic time differences into the system, which gives it impressive precision.
If the clocks in the satellites are running at a different rate, than the clocks down here on Earth, and you don't take that into account, you will get the wrong answer for where your car is.
Drive 0.1 miles to destination on left.
The distortion of time is only one of the strange results of traveling close to the speed of light. On the bike track, Clifford Johnson continues to push the envelope as space begins doing odd things to him and his bicycle.
Imagine I'm on my bike again, going close to the speed of light. An observer looking at me would actually see, for example, that the length of my bike in the direction of motion I'm moving is getting shrunk. Actually, the bike is getting shorter.
The effect is called length contraction, and together with time dilation, it is seen by a stationary observer while looking at someone traveling close to light speed. But Professor Johnson does get his own chance to witness light speed's weird effects. As his velocity closes in on light speed, his view of the world changes drastically.
What I'm seeing as I move close to the speed of light, straight ahead, is that the shapes in front of me are getting quite distorted as compared to everyday life. Everything is being twisted into a sort of tunnel shape, and the colors are getting distorted in various ways.
The color changes come from the Doppler effect, and the shape distortions from a phenomenon known as aberration.
The distortion is somewhat similar to what you would see if you were driving through a rainstorm. If you were stationary, you would just see the rain coming straight down if you looked out of the side of the window. Whereas if you were moving through the storm, you would see that the rain appears to be slanting towards you as a result of your motion. And that's at the basis of that warping effect that you get as you're moving near the speed of light towards objects in front of you.
In reality, we don't have to travel near the speed of light to experience the distortions caused by motion through time and space. They are with us every minute of the day.
All of the distortions that happen as a result of a finite speed of light still happen on an everyday basis, even in our everyday life, but the effects are so tiny that we can't perceive them.
Still, light speed has its other quirks in the slow-moving world, quirks we perceive very well. The speed of light may be a constant, but only in the vacuum of space. When light moves through things like glass or fluids, it slows down appreciably. If it didn't, things like telescopes and human vision would be impossible. But what would happen if light slowed down much more? If the speed of light were zero? Light speed is 186,000 miles per second. It is a universal constant, but a constant with a catch. It travels at that speed only in a vacuum.
Light changes its speed when it travels through different media. It travels more slowly through water. That's why you see refraction and bending and rippling of light when you're underwater.
Life as we know it would be very different if light didn't propagate at different speeds through different materials. For example, we wouldn't be able to see. Our eyes wouldn't work the same way.
In a universe where light moved at the same speed through all materials, we would know little of the world around us, seeing only vague blobs of dark and light. That's because our eyes depend on biological lenses to focus images on our retinas. Just like lenses made of glass, they work because light slows down as it passes through them.
Now, why is that? Because light is absorbed by the atoms of glass, and then they re-radiate it later. So there's a delay factor. Light hits an atom, the atom vibrates, and then sends a light package off. So there's a delay factor.
The delay factor also causes light to bend when it hits glass shaped into a lens. Bent in just the right way, light can be focused, collected, and magnified. For astronomers studying the universe, nothing could be more important.
Thank goodness light slows down when it goes through glass, because that's the reason why we have telescopes. The reason why we have telescopes is because light bends going through glass, and we can concentrate. concentrate large amounts of light to a single point, and then that gives us the ability to see the marvels in the universe itself.
Light travels through the glass lenses of telescopes at about 124,000 miles per second, 2/3 of its speed through a vacuum. But some scientists are looking at making use of light at far slower speeds.
And then we have the AOs over here. They're pretty much all functioning now.
At her lab on the campus of Harvard University, Dr. Lena Howe has taken slow light to the extreme by reducing light speed to 0.
The speed of light, of course, is incredibly high. I mean, nothing goes faster than light. And, you know, the usual 186,000 miles per second. And we kind of thought, gee, that's awfully high. Let's try to do something about it. So we have the detector right there.
Howe and her team conducted their experiments in a complex laboratory filled with lasers, mirrors, prisms, and other exotic gear. It is a branch of physics where few have dared to tread.
If you can start to change things so dramatically as taking this enormous light speed and then bring it down to bicycle speed, that then you're in a completely new regime of nature. You're able to now start to probe areas, regions of nature where nobody has ever been there before.
The brakes are put on light speed inside Howe's lab by focusing lasers on 2 microscopic clouds of sodium gas chilled to a few billionths of a degree above absolute 0. A control laser hitting the 2 clouds sets them up for action. Then, a quick light pulse shoots into the first cloud, where it is squeezed into the gas and slowed to just a few miles per hour.
The light pulse goes from being about 1 kilometer long in free space. It compresses like a concertina as it enters the atom cloud and ends up being only 0.02 millimeter in size. That's less than half the thickness of a hair. So really small, and it's so small that the light pulse actually ends up fitting totally inside the atom cloud.
Howe says the atomic imprint of light in the sodium cloud is a perfect copy, embedded in atoms, of the original light pulse. It can then be stopped in free space between the 2 clouds before moving on. When it enters the second cloud, another shot of the control laser expands it to its original size, shape, and speed of 186,000 miles per second. It is comparable in some ways to a science fiction transporter that sends people or objects through space.
So in these experiments, what we really do is we stop and extinguish a light pulse in one part of space and revive it in a completely different part of space and send it back on its way.
Since light can carry information, this super advanced technology points the way to futuristic light-based computers that bypass wires and electronic chips. Information read directly from light may be faster, more compact, and more secure than anything we have today. But the greatest vision of scientists and dreamers is to be found at the other end of the light speed spectrum. We still face the speed of light as an impenetrable wall, a speed that Dr. Einstein told us could never be exceeded. Yet history is packed with impossibles that have become realities. Will we ever, for instance, be able to reach the stars in ships that go faster than the speed of light? If so, when? In April 2008, world-famous physicist Stephen Hawking called on the human race to colonize space and make interstellar travel a long-term aim.
Spreading out into space will completely change the future of the human race, but maybe determine whether we have any future at all.
The stars are so far away that interstellar travel is impractical unless we can go faster than light speed. But that's an obstacle. Einstein's theory of relativity tells us that a spaceship's mass approaches infinity as it nears the speed of light.
So as you try to go faster and faster and faster, you actually get to a point where it takes more and more energy until it's an infinite amount of energy to go the speed of light. That's impossible.
It means that travel at light speed is also impossible. Or is it? Mark Millis is one of a handful of scientists who isn't ready to throw in the towel on the subject. A NASA propulsion physicist by profession, he likes to build models of starships in his spare time and is well aware of the giggle factor in any talk outside science fiction of star travel.
The giggle factor is actually a healthy response. It helps provide skepticism to the topic to ask deep questions to make sure that we're proceeding correctly.
Once head of NASA's mothballed Breakthrough Propulsion Project, Millis is editor of a book that has collected the serious current research on the subject.
When it comes just to the light speed issue, there's about 36 physicists who've written articles, some skeptical, some suggesting new methods on the topic.
No one is saying that anytime soon we'll be able to have warp drive to the stars. But on a scale of centuries to millennia, it can't be ruled out.
Virtually all physicists agree it's impossible to travel through space at faster than light speed. But there may be a way to cheat by altering space instead of traveling through it.
Believe it or not, even NASA scientists are studying the possibility that perhaps we can fold space, punch a hole in space, make a subway system through space and time.
That's the basic idea behind using wormholes to actually twist space around on itself and take a shortcut through the universe. What would a wormhole machine look like? Probably huge in scale, with equipment staged perhaps on a massive number of asteroids arranged in a gigantic sphere.
It would require an enormous battery of laser beams to concentrate tremendous energy to a single point. You have to attain fantastic temperatures, the highest energy attainable in our universe, in order to open up a hole, a bubble, a gateway, perhaps, to another universe.
Another way of tricking space into letting us travel faster than light is the warp drive.
Miguel Alcubierre was the first one to write about the warp drive in 1994.
Alcubierre, a Mexican physicist, worked out the math for a starship propelled by warping space-time itself. Behind the ship, space-time is expanded. In front of the ship, space-time contracts. In between, the ship rides like a surfer. The ship itself sits inside a bubble, and the space around it pushes it faster than light. A successful warp drive, if it is possible at all, is probably centuries away. But in Switzerland, physicists at the Large Hadron Collider may be headed in the right direction right now.
Now, the Large Hadron Collider is an atom smasher. It's a particle collider. But it's going to get to high enough energies that space and time will actually warp and bend. We're actually practicing how to bend space in the laboratory. It's the first baby step toward a warp drive.
With the physics we now know, we won't travel faster than light speed in the foreseeable future. That doesn't mean we shouldn't try.
Even though light speed travel might turn out to be impossible, to give up without trying is just giving up.
Outside his work at NASA, Millis has founded the nonprofit Tau Zero Foundation to encourage serious research on star travel. Although few scientists are pursuing the idea actively, many agree it's worth at least the effort.
Understanding our universe is one of the most basic needs human beings have as an intelligent species. So should we pursue technologies or physics that might allow us someday to travel faster than light? Absolutely. Because we never know where this might take us. Even though we might never discover a way to travel faster than light, we might discover a whole bunch of other very useful things.
And what if science ultimately proves the light speed barrier is unbreakable and star travel is impossible? It would put a whole new perspective on spaceship Earth, forcing us to use our technology to treat it well as we remain its passengers on our continuing journey through the universe.
In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
They roam the planetary surface, fly underwater, and soar through the heavens. But this is no wildlife safari on planet Earth. This is an expedition of astronomical proportions.
Everything looks good from here. Okay, we copy that.
When the human race discovers it is not alone, what will our cosmic brothers and sisters look like? To answer this question, leading astronomers and astrobiologists have applied the principles of evolution and physics to 5 types of alien worlds likely to be found in the cosmos. These are the creatures that could be out there. Prepare to take an intergalactic safari and peer directly into the eyes of alien faces. The universe. An intergalactic sanctuary of billions of galaxies and trillions of stars. Could it only be a lifeless, barren wasteland of gamma-ray bursts, burning stars, and black holes? Or does life exist beyond Earth in this cosmic paradise? Do alien faces gaze towards us, pondering the age-old question, are we alone? Scientists are still searching for the first signs of life beyond our planet, but many are convinced it's out there, waiting for us to find it. But what on earth, if anything, would it look like? With a potent mix of earth science, logic, and the theory of evolution, computer graphic artists are able to bring some of these alien faces to life. And to come face to face with these extraterrestrial creations, we will embark on a fantasy safari through the unexplored reaches of the universe, like a tourist in an intergalactic zoo. Our first stop, the theoretical planet Arenal.
The planet Arenal is an odd planet. First of all, it doesn't circle around a star like our sun. It circles around a little red dwarf. These are tiny stars. They're sometimes a fifth, a sixth the size of our sun. So the habitable zone is going to be much closer to that star.
This habitable zone is a crucial piece of the puzzle when understanding the evolution of life on any alien planet.
A habitable zone in a solar system is the distance from the star where water can exist as a liquid on the surface. It gets enough heat energy from the star to have liquid water and stay liquid water.
Liquid water is one of the basic elements for life to begin. But on Arenal, the habitable zone is so close to this glowing ball of burning gas The star's gravity causes Arenal to be tidally locked, much like Earth's moon, as we only see one side of the lunar surface at all times. This would mean that half of Arenal is constantly in daylight, and the other half is constantly in darkness. In the middle, there would be a 200-mile wide area that stretches from the North Pole to the South Pole, which is in a constant state of twilight.
So it makes you wonder, where would we find life on this planet? Well, truthfully, you're going to find it everywhere. But if it's on the dark side, it's life that's been adapted for living in the dark. And if it's on the bright side, it's life that's been adapted for living only in the bright side. And in this twilight zone area, you're going to find creatures that are adapted for both. They can wander and stray into both sides on this world. They really control their own destinies in where they want to go and where they want to hunt.
On Arenal, you're going to have a photosynthetic organism, probably likely in the marine environment, a red alga, or a bacteria that will be adapted to taking in infrared light and taking what energy it can out of that and making food. On land, it would probably be a lichen-like thing because it's cold, mosses that would be adapted that way. You're going to have organisms that are going to feed off those.
This algae on Arenal represents the bottom of a very long food chain. Everything plays a vital role for survival, from the plant life to the larger, more complex creatures. One example on Arenal that uses this algae as a food source is the insect known as an acom.
The acoms are a bizarre little creature. On Earth, we know of what we call metamorphosis. It's the odd ability of a creature to change from one shape to another. We see it in butterflies. A caterpillar eating in your garden will climb up on the fence, spin a cocoon, months later hatch out into a butterfly. These do that too, but they do it in a very odd way. They look almost eel-like with two sets of fins that stick out on either side. At some peculiar moment, they move over to some of the plant life, lock themselves in, and attach themselves and form a shell around them. When that shell splits, out comes something that we've never seen before. Taking the hydrogen from the water, splitting the hydrogen from the oxygen, it inflates a little bubble, and they lift right out of the water. The breeze is picking them up, carrying them to high altitudes, spreading them out over the planet towards the twilight zones as the breezes move, and they're almost like parachutists coming back down.
Once the acoms reach the ground, they immediately create a burrow where they primarily live. But as the acoms scavenge through the dirt for food, they're hunted from above by one of the next links in the food chain, the pinnipod.
Now, one of the creatures that we'd find most interesting on this world is the pinnipod. It's an odd little creature because its eyes wrap all the way around so it can see any movement behind it.
In the twilight zone of Arenal, it is going to be very dark and cold due to the low light of its star. And the hunters, or even the hunted, will have developed large eyes like owls or other nocturnal creatures here on Earth. But there's an interesting adaptation that developed in most creatures on Arenal.
Arenal orbits an M star. M stars emit most of their light in infrared. Infrared is the light that, it's actually heat that you feel when you open up the oven. That's what these creatures would see. They would see the heat expended by their bodies in the world around them. It would look very different than it does to you or me.
To see heat signatures on the dark side of the planet is one of the biggest links on the food chain of Arenal. The Kurja, a cunning advantage.
In their sense, in their moves, in the way they act together, they resemble jackals in the plains of Africa. They move in herds, they're hunters, they're predators. They're ugly little nasty creatures that will surround a pinnipod or a colony of them, ferret them out, and that's their meal. They have the odd ability, however, to see not only in the twilight regions with eyes like we might normally have, but they have a second set of smaller eyes right above that once they move into the darker regions, the nighttime side, they can now pick up the heat signatures of creatures in that area.
These are only a few of the creatures that could live on a planet like Arenal. But at least for now, they are simply a product of our imagination.
In science, we can sit there and we can imagine life elsewhere. But if we have examples, we have one data point, in fact, and that's planet Earth. And so if we can look at life on Earth, it provides us with an amazing wealth of information that we can then take forward to look for life elsewhere.
We have a variety of ecosystems that we can study, and we can look at challenges. What are in ecosystems? What challenges do living things face? And we can apply these principles to alien life.
To understand how these principles can be applied, we must continue our intergalactic fantasy safari. We leave the surface of Arenal and zip across the cosmos 322 light-years away to a new solar system and the theoretical planet AG-143.
AG-143 is bigger than the Earth, much bigger than the Earth. It has a beautiful ring system that circles around it. But more importantly, it is a big, gigantic, dry desert with 3 times the gravitational field that we feel here on the Earth.
A human weighing in at 175 pounds on Earth would step off onto the surface of AG-143 to weigh about 525 pounds. Certainly, life would need to adapt. But how? David Aguilar of Harvard University's Center for Astrophysics believes the best way to envision the adaptations of complex alien life forms is by looking at the variety of creatures that have evolved to inhabit the diverse ecosystems of our own world.
We're here at the North Carolina Zoo because of all the zoos in the country right now, this is very special. It is large. It's big. And the environments here duplicate the different environments we find on our planet. This here today is a marvelous example of the variety of life on our planet.
And within this variety of life on Earth, Aguilar believes that creatures supporting an extremely heavy structure become the perfect model for understanding evolution on AG-143.
When we talk about an animal adapted for a heavy world environment, a world with more gravity, this is it. Look at what we have out here, the prototype legs that can suspend a huge body. Of course, we would have to move him down, move him closer to the ground, but this is perfect what we would see. Shorter, squattier, but heavy like this, adapted to a planet with much stronger gravity.
Although life forms on AG-143 have certain comparable characteristics to creatures on Earth, their alien faces are beyond anything found on our planet.
Everything looks good from here.
Okay, we copy that. Sounds good.
I wish we were with you.
What if, one day, a deep space probe detects life outside our solar system? What would an alien look like? To better understand these otherworldly creatures and how they might have evolved, scientists believe you must first understand a few simple concepts about the physical environments where life might begin.
When looking at planets around distant stars, there are 2 factors that we scientists zero in on. First is distance to the mother star. That determines how much energy you have and whether or not you have liquid water. Second, the mass, the size of the planet. That determines gravity and what kind of organisms you may have.
When people think about evolutionary biology, we tend to think of the whole nature red in tooth and claw, the whole Darwinian competition among organisms and among species and so on, but we forget that it's the physical environment that really shapes life. What gravity you have, what temperature, what pressure, what composition the atmosphere is, if there is any atmosphere, and so on.
The laws of physics don't change as you travel through the universe. So understanding how creatures evolved in our earthly environment has allowed scientists to imagine what life forms might arise on other types of worlds, like the theoretical planet AG-143. AG-143 orbits a bright F-class star. Only 10% of this world is covered with surface water, and pockets of this liquid H2O collect under the sands from sparse rainfall. The environment on AG-143 is hot, arid, and the sunshine extremely bright.
Now, because the star is an F-class star, okay, which is brighter than the sun, you're going to have UV output, ultraviolet light output. So, the organisms there are going to have to somehow be shielded either in the atmosphere or in their own coverings.
These coverings may be in the form of thick shells or other exteriors that would absorb the harsh UV radiation. But the creatures on AG-143 would also develop other physical characteristics that are unique to this world.
It's really interesting to imagine what life might be like on a planet with higher gravity. Well, from a microbe's point of view, there might not be a whole lot of difference. Where the differences would start to come is when you go out and land, for example, and there you have to worry about standing up. Oh, darn gravity, you know, I just can't pull myself up.
But another byproduct of strong gravity may also give rise to an unlikely cast of characters on the surface of AG-143. Or rather, slightly above the surface. On Earth, our atmosphere is 79% nitrogen, 20% oxygen, and 1% other gases that is held in place due to the gravitational pull of the Earth. But on a planet like AG-143, the stronger gravity would hold a much thicker atmosphere, perfect for achieving flight. It may also hold a much higher level of oxygen.
We went through a period a couple of 100 million years ago where we think the Earth had a higher concentration of oxygen for a while. And what we see in the fossil record is giant insects, huge wings, giant flying organisms, because if you think about it, you have more oxygen for metabolism, so you can do things with more energy. It's like taking in a higher oxygen with an oxygen tank or something, and you feel all pumped up. And that's how these organisms must have felt.
With a thicker atmosphere and higher concentration of oxygen, the skies of AG-143 would be full of large flying creatures that could stay airborne for as long as they need. One example could be the sargon. This creature would live most of its life soaring through the atmosphere, looking for pockets of water that scarcely pepper the planet. Once the sargon finds a watering hole, they swoop down in hopes to not only drink, but hunt any creatures that may have found their way to the oasis. A creature like the moblant.
At first sight, you might almost mistake a moblot for a starfish. It has stubby little arms that it moves across the desert. But the odd thing about these arms is they have long tentacles that probe the sand for pockets of precious water that may be hidden. And the odd thing about this creature is if it finds a large pocket of water, it begins pulling the water up like it's pulling it up a well. And it grows in size, and it grows in size, and stores the water up like a camel does.
Adaptations to locate and store water are crucial for survival. To be stuck out in the middle of a desert, hundreds of miles from anything resembling a liquid, would be a death sentence for almost any Earth creature. The same would be true for life on our theoretical planet AG-143. This is why the Pholus lives primarily near the water deposits, so that it will remain close to this precious commodity.
One of the most bizarre creatures on AG-143 is the Pholus. They're short, squatty. It's a mouth supported by 3 legs on a pedestal platform that has scales underneath. It glides across the sand almost like a sidewinder as it moves. It has the uncanny ability to sense chemically whether or not its prey is nearby. It hunts around the edges of streams and small little lakes. And if it finds its prey, it suddenly stops, freezes, and camouflages itself so that it almost becomes invisible, waiting. Until a hapless creature moves and then suddenly, out it snaps. It's found its dinner.
And the Pholus's method of movement, gliding across the surface like a snake on grass, is another evolutionary characteristic caused by the stronger gravity of the planet. To slide with scales rather than lifting a leg would be a lot easier for any creature. That, and it offers a quiet advantage over its prey. They may never hear the Pholus coming. But as the food chain goes on AG-143, nothing is safe. For lurking in these pools of water lies a silent but deadly creature known as the Hethor. As we end our examination of the food chain on AG-143, we've seen the extreme challenges that creatures on a world with little surface water and higher gravity must overcome. But what if the planetary conditions were reversed? What if a planet had a suitable amount of water for life, but also a much weaker gravitational force? The answer might lie right above our heads, in the skies above the Earth. On our intergalactic safari, we've seen how leading astrobiologists used present-day Earth science to hypothesize about the size, shape, and behavior of creatures on an imaginary world with much stronger gravity than Earth. But what would happen if the gravity was much weaker? To find out, we lift off from the strong gravity of AG-143 to another planet 89 light-years away, GPC 925.
GPC 925 is smaller than the Earth. It's about half the size of the Earth. It's borderline for an Earth-like planet. And because it's smaller, it has less gravity. The star that it circles around is cooler than our sun, and because of that, it's a cross between frozen ice patches, green photosynthetic plants peeking through, and some bodies of water. It would look very much like the northern part of our planet. You get up towards the northern parts of Canada and Greenland. We call it the taiga areas. GPC 925 would be a very specific type of environment. You wouldn't find deserts on this world. You would find very few mountains actually on this world. It would be a world that was cooler, more preserved than what we see on our own planet. But beautiful just the same.
This world with much lower gravity could generate much larger, more elegant life forms. You know, I'm 6'6". Imagine how tall I could be if I had evolved in a world with a half or a third the gravity. Imagine what a redwood would look like in a world with lower gravity.
These types of gravitational effects on the surface life would shape and model different characteristics. It would also appear that on a world like GPC 925, much of that surface life would not be found on the surface at all.
Here we are in the aviary. Up in these trees are the remnants of the dinosaurs. This is what was left behind when the dinosaurs passed on. These birds are meant to fly. Their bones are hollow, their feathers locked together. These birds were meant to rule the skies. But on a low-gravity planet, this is what you would see that would rule the planet.
Because gravity is going to be light, flight is going to be very easy. And flight is something that's been done on Earth by a number of organisms in different ways. Bats stretch membranes between their fingers and create wings to fly. Flying squirrels put flaps out of their fur and glide that way.
But not everything on GPC 925 is comparable to creatures on Earth.
The strangest of the airborne creatures one could imagine are the loligars. Imagine floating sacs that almost look like inflated lungs, with long, long, long tentacles hanging down that drape along the countryside as they slowly move and float over the scenery. Heated by internal heat inside, the warm air inflates their sacs. They almost look like jellyfish floating through the air. And like jellyfish, they sting and grab anything that scurries over the ground in front of them. To see them moving, bobbing up and down in the wind like a herd of psychedelic jellyfish is something beyond what we can imagine. And yet here, it's quite common.
Even life on the ground would push the limits of science as we know it.
When we take a look at this world, think of the sway stacks. They look like they are long stalks that extend 15, 20, 30 feet into the air. Numerous ones coming up with a bulb on the end. They sway in the wind, but what's amazing is these aren't plants. These are animals, with roots that pick up and slowly move across the planet's surface and anchor themselves back down, swaying in the wind with a weight for any creature that happens by. As the creature moves by, the top of them, like little frisbees, shoot off and wedge into the side of the creature, into their leg, into their carapace, into their hair, stuck for the moment. As they move on, they reach a new area, they drop off, and they begin growing all over again. They're simply spreading their seeds with these tiny little discs flying through the air once they sense something moving by. On this planet, we see similar things with the plants and the weeds that grow here, but nothing to this size and extent. And the idea that we begin crossing plants that look like animals and animals that look like plants, this is a bizarre world indeed.
Creatures like the sway stacks and the loligars would enjoy an adequate amount of water on GPC 925. But what would happen on a world where there was even more water? A lot more. Specifically, a planet with no land whatsoever. A water world. Since we embarked on our intergalactic safari, we have seen the amazing life cycle of the ACOM on Aranel, the bizarre-looking Pholus on AG-143, and the floating loligars of GPC 925. All of these theoretical life forms on these imaginary worlds have been created by scientists based on knowledge about the development of life on Earth. But how would these creatures have gotten their start on these strange, far-flung planets?
The requirements that we know have to be there for life is based on the life that we know. And the chemistry that we think leads to the origin and evolution of life is carbon chemistry in aqueous or water solution. So we need liquid water, we need carbon, and we need nitrogen.
And you need some sort of energy, because life, even microbes, needs food. They've got to have some sort of metabolism, so you need some source of energy. Sunlight works pretty well, but it isn't the only source of energy, even on Earth.
For hundreds of years, scientists believed that sunlight was the only energy source for life. But within the past few decades, new findings showed they were wrong. Boiling water temperatures found around hydrothermal vents on the seafloor were once believed to be incompatible with life. But recently, scientists have discovered the areas around these black smokers are perfectly suitable for a flourishing underwater community. Instead of the sun, these creatures take their energy from the heat, gases, and minerals spewing from the vents. These highly tenacious life forms are known as extremophiles.
The existence of extremophiles broadens our aspects of what we think organisms can do and what we know organisms can do. In other words, if you look at all of the different kinds of environments that we find here on Earth, it ranges from extremely cold to extremely hot to acid to alkaline. Just about anything you can think of, and just about everywhere you find life.
The fact that life is found at all on Earth is due in large part to our position in the solar system.
We scientists used to believe that in order to get life off the ground on a planet, it has to be in the Goldilocks zone of the sun. Not too close, because water will boil, not too far, because water will freeze, but just right to have a liquid ocean out of which DNA can form. Well, that picture we now know is wrong. We now believe that even on icy moons of planets like Jupiter, it is possible to get life off the ground. Europa is the moon of Jupiter. It's covered in ice, but beneath the ice, there is apparently a gigantic ocean, perhaps stable for billions of years, containing liquid water.